Welcome to the bench, everyone. Grab a seat. Now, as junior technicians, you're going to be spending a whole lot of time elbow deep in circuit boards, tracing paths, troubleshooting hardware, the whole shebang. So today's explainer is dedicated to a tiny little component that quietly powers, well, almost everything around you. I mean, from the smartphone sitting in your pocket right now and the motherboards you're repairing, all the way up to rockets and satellites. We are talking about the complete story of the capacitor. Okay, let's dive into this. I want to start with a very real scenario you will absolutely face on the floor. Picture this. You've unplugged a power supply, the battery is completely removed, it's totally dead, right? You reach your hand in to pull a board and suddenly, snap, you get hit with a massive shock. So how on earth does a dead board bite you? Well, it's because of what I like to call the electronic ninja waiting silently in the circuit. That ninja is a capacitor, and understanding it, that is absolutely step one to mastering electronics. So here is our workbench agenda for today. We're going to start with the electrical water tank concept. Then we'll look inside the component itself and analyze its charging and discharging behavior. After that, we'll cover some absolutely critical safety warnings, talk about smoothing power, and finally, look at the technician's toolkit. Let's get to it. Section 1, the electrical water tank. Let's start with the absolute basics, right? Electrons naturally want to move. That flow is what we call current. But early engineers, they had to figure out a way to temporarily hold on to that charge. So think of a capacitor kind of like an empty water tank. If you start pumping water in, the tank slowly fills up, and the more water that enters, the more pressure builds up inside. Eventually, the tank becomes completely full. Now, instead of water, just imagine we're using electrical charge. That's exactly what a capacitor does. It doesn't hold charge forever like a permanent power source does. It just holds it for a short, crucial amount of time. It's really much like keeping water in a bucket until you need to pour it out. Section 2, inside the component. Now, when you physically crack a capacitor open on your bench, you'll actually find a surprisingly simple structure. It's basically two conductive plates separated by an insulating material right in the middle. We call this middle layer the dielectric. And you can think of this dielectric as an impenetrable wall. So when you connect a battery, electrons rush to one plate and they build up a negative charge. But because of that dielectric wall, they literally cannot cross over to the other side. So what happens? The opposite plate loses electrons and builds a positive charge. It's like people gathering on both sides of a wall. They can stand right next to it, but they just can't cross it. Now, what's really interesting about this is how it clears up the absolute most common rookie misconception. Beginners, they look at those plates and think the capacitor is just a literal bucket holding a bunch of loose electrons. Actually, it's not. Because those positive and negative charges are separated by the dielectric, a really strong invisible force forms between them. It actually stores energy in the electric field itself. That electric field, that is the true heart of the capacitor. Section 3, behavior, charging, and discharging. Now we really need to look at its personality, specifically how it behaves under power. Because guess what? Capacitors absolutely hate sudden voltage changes. When a capacitor is empty and you apply power, it's a lot like blowing into an empty balloon. At first, it's very easy. The electrons rush in and the current is huge. But as the charge builds, the electric field grows stronger and it starts to push back. It gets harder and harder to add more charge, just like a balloon resisting as it fills up with air. Eventually, the capacitor just says, okay, enough, I'm full. And the moment it reaches capacity, the current stops completely. This creates these beautifully smooth charging curves in our electronics, rather than these instant chaotic jumps. Let's look at how it handles different types of current. If you feed it direct current, or DC, the capacitor fills up, the balloon is full, and it completely blocks any further flow. Simple enough. But alternating current, or AC, that is a totally different story. Because AC constantly changes direction, the capacitor is continually charging and discharging over and over and over again. This constant movement means the current keeps flowing. It's almost magical. Capacitors will put up a literal brick wall to DC, but they'll let AC pass right on through. Section 4, warning, they bite back. All right, everyone, lean in for a second. This is the single most important thing you will learn before touching real hardware on the floor. I mentioned that electronic ninja earlier, right? Well, if you charge a capacitor and then totally disconnect the battery, that electric field, it is still there. The energy is trapped, just waiting silently. If your finger brushes across those terminals, your body becomes the wire. Pack. That stored energy instantly discharges right through you. If you've ever opened up an old disposable camera and accidentally touched the flash capacitor, you know exactly what I'm talking about. It is a terrifying jump scare.
It might be a tiny component, but it has a huge attitude. Always respect unplugged boards, and always discharge your large capacitors before you start working.
Section 5. Smoothing and filtering power. So you might be wondering, why do we even use these dangerous little ninjas? Well, because without them, our electronic world would be total unstable chaos. Think of them as tiny shock absorbers for electricity. One of their most critical jobs on the boards you'll be working on is in power supply filtering. You see, when we convert AC from the wall into DC for something like a computer motherboard, the output isn't just a perfect flat line. It's bumpy, kind of like rough ocean waves. Capacitors sit right there and absorb those ripples. They charge up during the voltage peaks and discharge during the drops, perfectly smoothing out that wave into a nice, stable flow. Honestly, if we didn't have them, the sensitive chips on your boards would crash instantly from the chaotic power delivery.
Section 6. The Technician's Toolkit.
So what hardware will you actually be handling day to day? First things first, burn this into your brain. A capacitor is not a battery. Amateurs confuse them literally all the time. A battery stores energy chemically, and it's designed to slowly drip feed power over a long period. A capacitor, on the other hand, stores energy electrically in a field, and it is designed to charge and discharge incredibly fast. We are talking fractions of a second. Think of it this way. Batteries are the marathon runners, capacitors are the sprinters, providing extremely fast, short bursts of energy. And this brilliantly illustrates what you'll find when you pull from your component bins. You're going to see tiny ceramic capacitors placed in your integrated circuits acting as these silent heroes to remove high-frequency noise. You'll see film capacitors used in precision audio gear. You'll even see supercapacitors holding massive energy for backup systems. But I need you to pay very close attention to the electrolytic capacitors used in power supplies. Notice the warning here. They are polarized, meaning they have a positive and a negative leg. If you solder an electrolytic capacitor in backward and apply power, it will literally explode. I'm serious, electronics will occasionally become fireworks if you aren't paying attention. So check your polarities. Beyond just power, you're also going to see capacitors teaming up with resistors to form what we call RC circuits. Because a capacitor charges slowly through a resistor, we can actually use them as timing devices to create intentional delays or, to make LEDs blink. In audio equipment, they're strictly used as gatekeepers, blocking that unwanted DC while letting the AC audio signal pass through perfectly so your music isn't all noisy or distorted. And this is wild. If you look under a microscope at the modern processors powering our computers, you will literally find billions of microscopic capacitors built directly into the silicon. They're invisible to the naked eye, but they are absolutely essential to communication and wireless technology. So we've covered the water tank analogy, the dielectric wall, the jumping electrons, and for sure the explosive dangers. A capacitor isn't just some basic piece of plastic and metal. It's a vital energy storage system, an electrical cushion, and a timing device, all rolled into one. Once you truly grasp how capacitors breathe energy in and out to stabilize a circuit, the boards in front of you, they stop looking like confusing maps of solder and start feeling truly alive. I promise, you'll never look at a motherboard the same way again. So as you head out to your workstations today and plug in your gear, ask yourself, what other invisible forces are quietly dictating the behavior of the technology sitting in your hands right now?